Hi students, good morning. Today I am going to explain about Einstein coefficients and relations. Okay, now it is from laser unit. So here first of all we have to consider two active energy levels. So that is it is E1 and E2. E1 is a ground state energy level, E2 is a excited state energy level. And here N1 and N2 are there. What is N1? N1 means number of atoms are present in ground state. N2 means number of atoms at excited state. So initially atoms are present in ground state. So after long time we have incident some photon of energy. The atoms are completely absorbs this photon of energy. Then it excites to higher energy state. But at higher energy state, the atom spends only a short interval of time. That is 10 power minus 8 seconds. 10 power minus 8 seconds. So after completion of this time, so the atoms are returns to the ground state energy level. Then it emits photon of energy. So it is an incident photon. It is an excited photon because it emits photon of energy. Then the atoms are returns to the ground state. So same thing here happen. So that means here I am writing here consider two energy levels of energy E1 and E2. E1 is a ground state, E2 is a excited state. So on N1 and N2 be the number of atoms per unit volume of E1 and E2. So in Einstein coefficients mainly we have three coefficients, that is B12, B21, A21. So first of all, the first one is stimulated absorption. Stimulated absorption means it is exist in ground state process. So usually the atoms are present in ground state. So after a long time we have incident photon of energy, then the atoms are completely absorbed at photon of energy. That is the stimulated absorption. So that stimulated absorption rate depends on the number of atoms in ground state energy level. Number of atoms are present per unit volume in a ground state energy level, and also it depends on energy density of photons. Energy density of photons, because here you have to incident photon of energy, that is the energy density of photons. So that's why stimulated absorption rate is depends on the number of atoms in ground state and energy density of photon. So that energy density of photon is denoted by rho of nu. So that's why it is proportional to N1 and also proportional to the rho of nu. So that's why it can be written as it is proportional to the N1 into rho of nu. N1 into rho of nu. So if you want to remove the proportionality term, then we can equal here it is equal to the B12 N1 rho of nu. B12 N1 rho of nu. Here B12 is known as Einstein coefficient of stimulated absorption. Einstein coefficient of stimulated absorption. And second thing, spontaneous emission. So the spontaneous emission is, already you know that the emission takes place without supplying of energy is known as spontaneous emission. So that's why the spontaneous emission rate depends on the number of atoms at excited state. Number of atoms at excited state. But in case of spontaneous emission, there is no incident of photon of energy. So that's why it is independent of incident photon. It is independent of photon of energy. So that's why it is depends on the only number of atoms on excited state. So that is it is proportional to the only N2. It is independent of rho of nu. So that's why it can be written as it is equal to the N2 A21, where A21 is called as Einstein coefficient of spontaneous emission. Einstein coefficient of spontaneous emission. And third one, let us consider stimulated emission. The stimulated emission is depends on the number of atoms at excited state as well as energy density of photon. Because energy density of photon means in case of stimulated, the emission takes place with the supplying of energy. The emission takes place with the supplying of energy. So that's why the stimulated emission is directly proportional to the N2 and also rho of nu. So it can be written as it is proportional to the N2 and rho of nu. So then it is equal to B21 N2 rho of nu, where B21 is called as Einstein coefficient of stimulated emission. Einstein coefficient of stimulated emission. So now we have three Einstein coefficients. One is A21, another one is B12, and last one is B21. Here we have two types of process. One is absorption process and another one is emission process. So a thermal equilibrium, the upward transition is equal to downward transition. That means the absorption process must be equal to emission process. So absorption process must be equal to emission process. So here the stimulated absorption is equal to stimulated emission plus spontaneous emission. So what is the equation of stimulated absorption? We know that previously B12 N1 rho of nu, and stimulated emission is spontaneous emission is A21 N2, and stimulated emission is B21 N2 rho of nu. So it is the equation. So in thermal equilibrium, both the transition must be equal. That means upward transition equal to downward transition. So that's why I can write this equation. Now it can be written as just B12 as usual N1 rho of nu minus B21 N2 rho of nu is equal to A21 N2. Here the common term is rho of nu. If we take rho of nu is common, then we get B12 N1 minus B21 N2 is equal to A21 N2. Then it can be written as in terms of rho of nu. Rho of nu is equal to A21 N2 by, here it is multiplication and this here it divided. So divided by B12 N1 minus B21 N2. Here it is A21 N2. So here the common term, we have taken the common term is N2 B21. If we take it is common N2 B21, then it can be written as N1 B12. Here there is no N2 B21. So that's why I have written as here N2 B21 in denominator minus 1. Okay now. So in case of population inversion, already we have studied in case of population inversion, the Boltzmann distribution law. According to Boltzmann distribution law, we know that N1 is equal to N0 exponential function of minus E1 by KT. N2 is equal to N0 exponential function of minus E2 by KT. So then from that equations we can write N1 by N2 is equal to exponential function of E2 minus E1 by KT. That is equal to exponential function of h nu by KT. Okay, where K is a Boltzmann's constant. K is a Boltzmann's constant. T is a temperature. Okay, so substitute N1 by N2 value in the previous equation. So previous equation means what is that? This is the equation, previous equation, rho of nu. So in the place of N1 by N2, we can substitute exponential function of h nu by KT. Then it becomes rho of nu is equal to A21 by B21 into B12 by B21 exponential function of h nu by KT minus 1. Okay. But according to the Planck's quantum theory of radiation, there is a one formula. That formula is the energy density of photon is equal to, this is the formula, 8 pi h nu cube by c cube exponential function of h nu by KT minus 1. Where h is Planck's constant, nu is frequency, c is a velocity of light, k is a Boltzmann's constant, t is a temperature. So if you compare these two equations, so it describes energy density of photon. It is also describes energy density of photon. So we can compare these two equations. So in the place of A21 by B21, here we have 8 pi h nu cube by c cube. 8 pi h nu cube by c cube. So next to, in the place of B12 by B21, there is no anything. In the place of B12 by B21, there is no anything. If there is no anything means we can write 1. So from this equation we can write A21 by B21 is proportional to the frequency cube. because phi is constant 3.14 value, h is constant, Planck's constant 6.626 into 10 power minus 34, c velocity of light, it is also constant. Okay now, so these terms all are the constant, it is the frequency is variable, that's why I have written as A21 by B21 is proportional to the frequency cube, and from this equation we can write B12 is equal to B21. So here these two relations are Einstein's relations. That means the first relation can be said that the relation between Einstein coefficient of spontaneous emission to the stimulated emission is directly proportional to the frequency cube. That is the first relation. And second relation is the Einstein coefficient of stimulated absorption rate is equal to Einstein coefficient of stimulated emission rate. So these two are Einstein relations. So Einstein coefficients are B12, A21, B21. These three are Einstein coefficient. But these two are Einstein's relations. So it is about the Einstein coefficients and Einstein relations.